Welcome everyone. In today's session, we will discuss about set theory and their application. In this session, mainly I will be focusing on the basic concept of set theory and their application. Let's start with basic definition of set theory. What is set? Set is a collection of well-defined distinct objects. Set is the collection of well-defined distinct object, that is nothing but set. What does it mean by distinct object and well-defined? Well-defined means this should be defined properly. Like if we take an example like 1, 2, 3 in a set, and mainly whatever the object we write in set, we write under curly braces. And each object of the set theory will have a unique meaning and it should be well defined. For an example, if I take 1, 2, 3 in the curly braces, this will be set because each object of this set are well defined. What about 1, 1, 3? This is not set because this is not unique. In this set, all the elements are not unique because 1 appears twice. So this is not a set. Again, if we take this example, look at this example. Number of good doctors in the hospital. Number of good doctors in the hospital, it can never be a set because good word is not well defined. Good word is not well defined because it varies person to person. If I say someone good, other people may not say that person good. So good is completely depends person to person. So this is not a well-defined word. So this is not a set. Now, what we need to note under the set, the order in which elements are written between the curly brackets does not matter at all. What does it mean? Like if we consider 1, 3, 5, and 7, 9, if someone writes like this, even if we write these same things in the different order, like say 3, 5, 1, 7, and 9, these are nothing but same. So order in the set does not matter at all. And if we see any object or element in the set repeat twice or thrice or more than once, so to make this as set, what we will do, we'll write these both element only once, and this will become set, but this is not set because in definition itself it says well defined and distinct object. So this should be well defined as well as distinct. Now let's see different types of set. How different types of set, different way to represent set. First is statement form. Statement form, in this well-defined descriptions of the elements of the set is given and the same enclosed by the curly braces. Like, see, the set of odd numbers. This is completely, you can say, like, if anyone say odd numbers, that means we will start from 1, 3, 5, 7, 9. So this is a well-defined word. So this is obviously a set. And in this statement form, we write like this: odd numbers between less than 7. Odd numbers less than 7, that means odd numbers are less than 7, that means 1 2 sorry 1 3 5. These are the numbers which are odd and they are less than 7. So this is obviously a set. And if we write like this is nothing but the form of statement form. Now what about roster or tabular form? Roster or tabular form, we write each elements like this. See, elements of the set are listed within the pair of brackets and separated by commas. This is statement form, and if we write like this is nothing but a roster form. Now see, this is important. Usually we use this form to describe set. Mainly we use this and the next one, that is set builder form. This is also we often use this form. In this form, we write like this: x such that x is counting numbers greater than 12. So in this set builder, if we convert this in roster form, x is a counting number greater than 12. Counting number means nothing but a natural number greater than 12. So we'll write 13, 14, 15 and dot dot. It continues. So this is a counting number and greater than 12. We can write like this, and set builder form we'll write like this. Now we'll see different types of set. What is finite? The word finite means it indicates that we have some elements in the set which are finite number of elements. Say suppose we include some numbers like 1 2 3 4 5. So obviously there are finite number of elements. We can count the numbers, like how many numbers are there, we can easily say. So this is nothing but a finite set. So what is finite set? Finite set means it should have finite number of elements. Then we can say this is a finite set. I have given some example. Whole number between 2000 and 2005. So there are only 4 whole numbers between 2000 and 2005. That is 2001, 2002, and 2003, and 2004. So obviously there are 4 number of elements. So this is a finite set. Again, I have given another example, that is 2000 to 3000. The whole numbers between 2000 to 3000. So there are how many elements we can count? Obviously there are finite number of elements. So this is a finite set. Now about infinite set. This is exactly opposite to the finite set. In this set, the number of elements are infinite. There are a lot many numbers are there in the set. We cannot say how many exactly numbers are there. So that is why this is a infinite set. Suppose say even whole numbers. So there are a lot many even numbers. We cannot say how many even numbers are there in this set. So this is why it's an infinite set. Whole numbers greater than 2000. Again, this is a infinite set because there are so many numbers more than 2000. So this is infinite set. cardinality. This is important. Cardinality is nothing but total number of unique elements or objects in the set. See, in this set, how many elements are there? We can count 1, 2, 3, 4, 5, 6, 7. So total number of elements 7. So this is cardinality of A is 7. And cardinality is defined of any set, like say for a set A, the cardinality usually is defined as n of A or mod of A. For an example, if we take A comma B comma C comma D, and this is, let's say the set is X. So what is the cardinality of this set? 1, 2, 3, 4. So cardinality of the set is 4. So simple. What about the next one? It says A is a set X such that X belongs to integer set. We can say there are lot many integers like 0, plus minus 1, plus minus 2, plus minus 3. So many numbers are there in this set. So obviously cardinality of this particular set will be infinite. We cannot say how many integers are there in the set. There are so many integers are there. So cardinality is infinite. Now empty set. The word itself, it defines the meaning of empty set. Empty means nothing is there in the set. Completely null. This is also known as null set or void set. A set having no elements is said to be empty set. I have given one example, like whole numbers between 20 and 21. Obviously, there are no whole numbers between 20 and 21. So this is empty set. Again, if we take x square plus 1 equal to 0, x square plus 1 equal to 0. That means x square equal to minus 1. And we know square of any real numbers will always be positive. Square of any real number will always be positive. So we cannot find any number whose square is minus. So this is empty set. Now singleton set. A set having only one element is known as singleton set. And also null set is defined as this phi or empty brackets. But if we write this phi in the curly brackets, this will become an element of a set. So this is an example of singleton set. Again, I have given another example, integer between 2 and 4. So what are the, this, if it's 2 and 4, in between the numbers 2 and 4, there is only one integer, 3. So x contain only one element, that is 3. So there is only one element. So this is singleton set. Now subset. This is really very important. Subset and proper subset. You need to properly understand what is meant by subset and proper subset. Subset A and B be two sets. Then set A is said to be a subset of B if its element of A is also an element of B. I have given one example. Owls are subset of birds because every owls are birds, obviously. So each element of this set contain in this set. So owls set of owls is subset of set of birds. Same way, if we define, like say A contains 1, 2, 3, 4, 6, 7, 5 till 100, and the set B, it takes only even numbers till 100. So each element of the set B contain in the set A. So this is subset of B, subset of A. Even if we take, like, let's say 1, 2, 3, we can say this is also subset of 1, 2, 3. It is also correct. Each element of the set, this set 1, 2, 3, it contains in the another set 1, 2, 3. So this is subset of that. But in the proper subset, it says X is a proper subset of Y if and only if each element of X should be in Y and there is at least one element in Y which is not in X. Same thing. I have taken the example so that you can clearly understand. 1, 2, 3 to 100 and 1, 2, 3 to 90 I have taken. So each element of B is an element of A. So B is proper subset of A. But here if we take A is 1, 2, 3 and B is 1, 2, 3, we cannot say A is proper subset of B. We cannot say, because we should have at least one element in B which should not be in the set A. But here each element of A is in B, again each element of B is in A. So we cannot say A is proper subset of B. So there is only one difference between subset and proper subset, is this one. In this, they have not mentioned that at least one element should not be in the superset. Even if we take A for an example, let me give you another example. A equal to 1, 2, 3, 4. B equal to, let's say, 1, 2, 3, 4, and 5. Here, each element of A is in B, but at least one element of B, that is 5, which is not in A. So we can say A is proper subset of B. Clear? So this is the main part of subset and proper subset. You should understand properly. In the proper subset, this B is known as superset. The bigger set is known as superset and the smaller set is known as proper subset of the bigger set. And note, every set is subset of itself. Every set. I have just said before. Let's say A is 1, 2, 3. So A is subset of itself. Every set is subset of itself. Empty set, subset of every set. Empty set is subset of every set. That means empty set means, I have just told you before, empty set is denoted as phi. It is subset of every set. Let's say A. And A is nothing but 1, 2, 3. So empty set is subset of every set. Now, this is important. Total number of subset having n elements of a set is 2 to the power n. So if total number of subset having n elements of a set is 2 to the power n, and total number of proper subset of having n elements is 2 to the power n minus 1. What does it mean? Let me give you one example. Give me a minute. Now, I have just skipped, that is power set. Power set. This is very important part, power set. We need to understand properly. Power set is set of a set. Set of a set. Like, let's say A, that is 1, 2, and 3. Power set usually denoted as P of the set A. How we can write? We need to write all the possible subset of A, that is 1, 2, 3. All the possible subset. How many possible subset we can define? We have just seen the note. Every set is a subset of itself, and every empty set is a subset of every set. Now, first is empty set, and we can take each element and make a set. So 1, 2, they are making set. If we write in the curly braces, they will make a set. 1, 2, 2, 3, and 1, 3, and the set itself, that is 1, 2, and 3. So this is a power set. Power set means what? The all possible subset of a set. That is nothing but a power set. More than this subset are not possible to define. So how many elements are there in the power set? 1, 2, 3, 4, 5, 6, 7, and 8. How many elements are there in the set A? 3. So how many possible subset we got? 2 to the power 3, that is 8. So we have noticed, if the set A has 3 elements, that is the cardinality of A is 3, then the possible subset of the set A will become 2 to the power 3. Now, if you take an example, let's say A have 5 elements. What is n of A? Then 5 elements. So n of A is 5. So what is total subsets? Total subset will be 2 to the power 5, that is 32. Different way, if we ask how many elements are there in the power set of A, that will be also nothing but 32. Now, in the proper subset, we have studied at least one element less. We should eliminate one element from the set. Okay, then we can say that is a proper subset of this. So, see, just look at the set A, that is 1, 2, and 3. Each of these 1, 5, 2, 3, 1, 2, 2, 3, 1, 3, they are proper subset of the set A, but this is not a proper subset of the set A. So how many elements how many proper subsets are there? Proper subsets will be 2 to the power 5 if a set have 5 elements, so 2 to the power 5 minus 1, so 31 proper subset. And in this set A, how many proper subsets are there? Proper subset, 2 to the power 3 minus 1, that will become 7. That's all. Now let us solve one interesting question on this proper subset questions. Let me erase this. Now, let's say A is 5. Let's say A is 5. So what is P of 5? P of A? That will become set 5. What is P of A? That will become phi as an empty set and the set itself. What is P of A? Phi as an empty set. This phi element, this will become an element, and this again, this will come and the set itself, the whole set. Observe it properly. This was an element of the set P of A. So I put another curly braces to make that element as a set. Now the set itself. So these are the elements of P of A. I think power set is clear for you guys. Now see equal sets. Two sets A and B are said to be equal if they have exactly same elements. Exactly same elements should be there. See here 1, 2, 3, 5, 7. 7, 5, 2, 3, 1. 1, 2, 3, 5, 7. Each of these two sets A and B elements are same. That is why these sets A and B are equal. Also, in the subset we have seen, like I have given one example like this 1, 2, 3, and another example I have taken 1, 2, 3, and I have said A is subset of B. Here again we can say B is subset of A. So another way to say equal set, if A is subset of B and B is subset of A, then A equal to B. Right? Okay. Now equivalent set. Two sets are said to be equivalent if they have same number of elements. Only in the given sets we need to see if those sets have equal number of elements. If that is there, that satisfies, then we can say those two sets are equivalent. That means I have given one example. A is a set x comma y comma z. How many elements are there? 3 elements. In the set B, that is ABC, 3 elements. That is why A is equivalent to B. But we cannot say these two sets are equal. We cannot say. Previously, I have given example. A is 1, 2, 3. B is 1, 2, 3. So can we say these two are equivalent? Yes. Because here is also 3 elements, in this set also 3 elements. So what we have come to the conclusion? Equal sets are equivalent sets, but equivalent sets may not be equal set. We have seen here. Here A and B, let's say A is, let's say 1, 2, 3, and B is A comma B comma C. Here obviously these two sets have equal number of elements, but we cannot say A equal to B because each elements of the sets are not same. So this is not equal set. And now it is universal set. Universal set, obviously it is not unique. The set under the discussion or set containing all the values in the given frame of reference is said to be universal set, and it is usually denoted as U or X, somewhere it is E. Now another important part of the set theory, that is union of set. What is union? Union of a set is nothing but set of all elements in the listed sets. For an example, if we take A and B, two sets, A union B is the set of all elements in A or in B. Let's say for an example, A equal to A, B, C, 1, 2, 3, and B equal to A, comma 1, comma 2, comma 5, comma 7. What are the union then? A union B equal to, I have written X in A or in B. Now let us first see the common elements. A, 1, here is also 1, 2 and 2. Common elements will be picked only once in the union. That is A, comma 1, comma 2. And the remaining elements, all the remaining elements, B, C, 2, 3. B, C, and 3. 2 we have already taken, so we cannot take again. And in the second set, 5 and 7. So this is union. In the Venn diagram, if we see this part, especially this part is nothing but the intersection, means this part the common. Like here we have seen A is 1, A1 and 2. These are the common part. So this will be here A1 and 2. This is the Venn diagram. We have taken A1 and 2. The remaining part B, C and 3. So we'll write here B, C and 3. What about in the set B? We have taken A1, 2 in the common part, A1, 2. So 5, 7 is the remaining. This is the Venn diagram. In this common region, we'll write only ones. Those are common in the set A and B. And whatever we see in this diagram, in this, that is nothing but whole part. This is nothing but the union. Clear? Okay. We can go to the next one. Intersection of set. I have just previously mentioned the common part is nothing but the intersection. That means what? Let's say for an example, A is 1, 2, 3, 4. B is 2, 3, 5, 7. So intersection is defined as A intersection B. We will take only the common elements. Only the common elements. 2 is common here. 3 is also common on the both set. So this will be written 2 and 3. So this will be 2 and 3. So this is nothing but the intersection. Union will take all, including the common elements and other than common elements. In the intersection part, we will take only the common elements of two sets. Now disjoint. Two sets are said to be disjoint if they do not have any common elements. I have given example 2, 4, 6, 8 in the set S, and in the set T 1, 5, 3, 7. In these two sets, there are no common elements. So these two are disjoint sets. I can give you another example. ABC, let's say one set, and another set is B, X, Y, Z. So these two sets are disjoint because they do not have any common elements. So null set. Intersection will be null. Then we can say two sets are disjoint. Clear? Now difference of sets. This is very important, and do remember all this symbolically that I have written from the union part. This symbolically we have to remember. This part we have to remember that I have written A intersection B. For the union also I have written. And the difference of two set, will write X as that X in A and X not in B. That means if we take an example, A, let's say 1, 2, 3, 4, 5, 6. And B, if we take 3, 4, 6, 7, 8. So A minus B will take the elements in A but not in the B. That means we should eliminate from the B and A the common elements. That is 3 and 4 are common elements, and also 6. 3, 4, 6 elements we should subtract from the A and we'll write it in the set form. That is 1, 2, 5. 1, 2, 5. This will become A minus B. So that means what? The set in the elements in the set A but not in the B. That means elements of B will be subtracted from the elements of A. If there are no common elements, so A minus B will become A. If we write, let's say, here it will be 3, 4, 5, and in the set A, here it will be 1, 2, sorry, not 3, 4, 5. This is 3, 4, 6. 1, 2, and 5. And in the set B, that will become 7 and 8. That means what? Element of A minus B means what? Elements of B will be subtracted from the A. So will remain 1, 2, and 5. If they would have asked like B minus A, so the set A will be subtracted from B. That means will remain 7 and 8. That is nothing but the difference of two sets. Complementary is almost like difference of two sets. Complementary complement of a set, let's say this is an universal set. This is universal set and this is set A. So A complement will be written as U minus A. That means the elements in U by or universal set, the elements in the universal set but not in the set A. For an example, let's say for an example, in the universal set, I have written 1, 2, 3, 4 till 5, 6, 7, 8. I have taken universal set as 1 to 8 and the set A, let's say 2, 4, 6 and 8. So we have just seen in the difference of two set, what we have seen? The set A will be written here 2, 4, 2, 4, 6 and 8, and in the universal set other than 2, 4, 6, 8, just means mark 2, 4, 6 and 8. So there will be 1, 3, 5, 7. So what is A complement? A complement is nothing but what? U minus A. U minus A. That means the set U, from the set U we shall subtract the set A, that is 2, 4, 6, 8 we shall subtract, so we'll get 1, 3, 5, 7. That's all, complement of a set. Now this is very important part, closed interval. Closed interval. Closed interval is an interval which includes all its endpoints and all the numbers between these endpoints and denoted in the square brackets. Let's say 1, 2 closed interval. That means if we draw a number line, let's say 1 and 2, this will be closed, and 2, all the elements between 1 and 2. We can get 1 between 1 and 2. There are many numbers in the set. So this will start from 1 to 2. That means x such that x less than or equal to 2 and greater than or equal to 1. If you say 1.5, that is there in the set. 1.1, that is also there in the set. 1.001, that is also there in the set. 1, that is also there in the set. 2, that is there in the set. But more than 2, that is not there in the set. Less than 1, that is also not there in the set. Closed interval means the endpoints will be included in the set, and between the endpoints, all the numbers will be included in the set. Open interval, the endpoints will be not there in the set. Just keep like this. Let's draw a number line. let me take 1 here and 2 here. Put the open balls or open circle on 1 and 2, because that means other than 1 and 2, other than the endpoints 1 and 2, all the numbers will be included in the set. So this will be represented as x such that x strictly less than 2 and strictly greater than 1. That means between all the numbers 1 and 2, other than 1 and 2. Clear? Okay. Now, semi-closed or semi-open, this is very easy. I will give you one example. Let's say 1 and 2 here, where it will be closed. Let's say 1 is closed, 2 is open. That means this will be closed and this will be open. That means what? This is nothing but x such that x is strictly less than 2 and not strictly greater than or equal to 1. That means 1 is included in the set but not 2, and between 1 and 2 each now all numbers are included. This is for 1 closed, 2 open. Let's say this is 1 and this is 2. 1 open, 2 closed. So 1 open, 2 closed means 1 open, 2 closed. That means elements strictly greater than 1 and less than or equal to 2. That means 2 is included in the set but not 1. Clear? Okay. Now I have listed some important results that we need to remember. A union phi equal to A. If we take let's say A is a set 1, 2, 3. If you take A union phi, that will obviously A, because in the set phi, that is nothing but a null set. If you take union with that, obviously you will get the set A, but intersection will be different. Phi, there is no elements, but A, we can take some elements, and if we take with the intersection, that will become phi. Idempotent law, that means if we take union with the set itself, you will get the set itself. Intersection with the set itself, you will get the set itself. And commutative law, that means set A union B equal to A union B. This will be B union A. And A union intersection B is B intersection A. Associative law, A union B union C will be associative. Just shift the brackets and take with C. These are the same. You just need to remember this formula. Distributive law, A union B intersection C is nothing but A union B intersection A union C, and A intersection B union C is nothing but A intersection B union A intersection C. Universal set and its complement, obviously it will be phi. Universal set and its complement will become phi, and null set, complement of the null set will become universal set. Complement of a set, and if you take again complement, you will get the original set. A, if A is subset of B, then B complement will be subset of A complement. A union A complement equal to X, where X is an universal set, then and A intersection A complement will be phi. Now I will explain De Morgan's law. A union B complement equal to A complement intersection B complement. A intersection B its complement equal to A complement union B complement. N of A union B, that means cardinality of A union B. Cardinality of A union B. Let's say this is A, this is B. And if we take the cardinality, that is nothing but this whole part. How we will take? If these two are disjoint, these two are disjoint set. So the cardinality of this and this, if you add, you will get n of A plus n of B. What if they are not if they are not disjoint? If they are not disjoint, let's say A and B. Let's say this is A and this is B, and they are not disjoint, means intersection exists. If intersection exists, if we count n of A means the all cardinality of A, that means this part is counted once. Again, if we are counting n of B, this part will be counted twice. This part will be counted twice. But union, I have told you, in the union part, there will be only one time, it will be counted only one time. So at one time will be subtracted to get the cardinality of union. And this part n of A minus B, n of A minus B, let me tell you this n of A minus B. This is A and this is B. A minus B, I have told you just this part, just this part. And to count the cardinality, what I have written, n of A, I have taken all the elements, I have counted all the elements of A, and then I have taken intersection, and we have subtracted those n of A from n of A. I have subtracted n of A intersection B, means this number of elements. If we subtract, you will get n of A minus B. In different way, we can also say this. We can also say this different way. Take intersection, take union, n of A minus B. I have counted in the union n of A union B, and then I have subtracted B. We'll get n of A minus B. This part will be n of A minus B, right? So there are many ways to write. I have written one part, and also I have given you another result. You can search your own way another result if it is possible. Obviously, there are some other ways to find the cardinality of A minus B. Same way, we can tell, like, if we can count B minus A also. This is B minus A, just this part. This is A, this is B. So n of B minus A will be n of B, cardinality of B, and then subtract the intersection. You will get n of B minus A. And the last part, that is n of A intersection A union B union C. Just look at here how to remember this. This is A, this is B, this is C. Now I have counted n of B means full part. I have counted. I have counted all the elements n of A. Now n of B means I have counted this whole part. Now n of C means n of C. I have counted this whole part. Now just look at in the diagram. Look at in the diagram. N of A I have counted, n of B, n of C. Just see the intersection of A intersection B, this is counted twice. But union, it will be counted only once. So I have subtracted one part. And again B intersection C, this part is already counted twice. So we can subtract one part. Same way, A intersection C, this is counted twice. So we can subtract one part. After subtracting all this part, the part this is subtracted 3 times. We have counted 3 times and then subtracted 3 times. So that part will be eliminated. That is why we should add only once. Then we can get the required result for A union B union C. That's all to remember from the set theory. These are the basic concepts and ideas, what are the definitions and what are the things we need to know. These are the complete set theory part. In the next session I will discuss the questions, different type of questions and the applications. Thank you.